Okay, so we're going to do question 7.20. So in this question again we have a capital as utility function u as a function of x and y equal to x power alpha y power 1 minus alpha. So consumer has an income of 60 to spend, and the price of good x is 2, while the price of good y is py, and that can vary. Okay, so we do not know the price of good y. And so part A of the question asking you to show the demand for good y equal to 60 times 1 minus alpha, everything divided by py. So basically what we have to do is to find the most preferred affordable bundle of consumption for the consumer given the prices in the income and the utility function. Okay, for good y. Okay, and therefore showing that the demand for good y is going to be a function of the price. So what we have to do first of all is to write out a budget constraint first. Okay, so anytime if you do not know what to do, you write out a budget constraint first because we are going to use it anyway. Okay, so I got px times x plus py times y, and it has to be equal to income. So in this case I got 2x plus py times y, and that equal to 60. Okay, so I'll call this is the star equation. Now I want to find the optimal bundle again. Okay, so because that is going to be the demand for my goods. Okay, because that is the bundle the consumer would like to consume, and so therefore another name for it is the demand function. Okay, alright, so the optimal bundle is going to be the bundle at which marginal rate of substitution is equal to the negative of the price ratio, just like what we did before. Okay, again remember if we use px, so I would say this is negative of the relative price. Okay, so marginal rate of substitution, if we use MUX on MUY, then the relative price has to be PX on PY. Okay, if you are using MUY on MUX, then the relative price has to be PY on PX. Okay, so what we have to do is just to find the marginal utility of x and y first. So given the utility function, the marginal utility of x is just going to be the differential of the utility function with respect to x. Okay, so again we have we're treating y as constant, so the power y to the power 1 minus alpha will just remain the same in front as a constant. And if we differentiate x to the power alpha with respect to x, then we are just going to apply the power rule where we move alpha to the front times x to the power alpha minus 1. Okay. So very similar, marginal utility of y is just a differential of the utility function with respect to y. And so if we differentiate a capital S utility function with respect to y, we are treating x as constant, so x to the power alpha remain the same in front, and we multiply by 1 minus alpha, y to the power 1 minus alpha minus 1. Okay, so that's just the power rule again. So if I simplify this, we're going to give me 1 minus alpha, x to the power alpha, y to the power negative alpha. Okay, so therefore my marginal rate of substitution is just going to be okay, so if I substitute that into my equation over here, okay, so I'll call this is double star. Alright, so the double star equation will become negative, so negative and negative sign, which is cancel out, so I will just not write it down again. Okay, so MUX is alpha x to the power alpha minus 1, 1 to the power 1 minus alpha, and MUY just 1 minus alpha, x to the power alpha, y to the power negative alpha. And it's going to be equal to the price ratio, which is equal to 2, which is px on py. Okay. Alright, so over here, alpha on 1 minus alpha would just be there. Okay. Now x to the power. So if I move, so I want to get rid of a negative sign, so y, so I keep y to the power 1 minus alpha the same. Okay. And if I move y to the power negative alpha to the numerator, I should be able to get rid of the negative sign. So that's become multiplied by y to the power alpha. Okay. And on the denominator, I got x to the power alpha remain the same. And if I want to move this x to the power alpha minus 1 to the denominator, it will become x to the power negative of alpha minus 1. Okay, because when you move to the denominator, it will change the sign, so it's become negative. Okay, and so on the right hand side, still 2 on py. So what I have here is alpha 1 minus alpha. Over here I got y 1 minus alpha plus alpha, which is applying just the power rule, and over here I got x alpha minus alpha minus 1 equal to 2 py. So what I got is alpha on 1 minus alpha. Now negative alpha plus alpha just cancel out. Okay, so I got y. And on the denominator, x alpha minus alpha cancel out, negative become plus 1, so that it's just x to the power 1. Okay, so 2 on py. So therefore I got y equal to 2 py Okay, so if I multiply one minus alpha on alpha, okay, to both sides of this equation, then I get alpha 1 minus alpha, yeah, times y on x times 1 minus alpha on alpha, and it's 2 py 1 minus alpha times alpha. Okay, so if I multiply 1 minus alpha on alpha to both sides of this equation, so the purpose of doing this is just to get rid of this alpha on 1 minus alpha over here. So as you can see, this will cancel with this will cancel with this. Okay, so what I have left is y on x equal to 2 py 1 minus alpha on alpha, and so therefore I have y is just going to be equal to 2 on py 1 minus alpha on alpha times x. Okay, so this is my 3-star equation. Okay, so in order to find the optimal amount of wood Y, which is to show the demand for wood Y, then I will just substitute. Okay, sorry, so I want to show I want to show wood Y, so I'll try not to get rid of. So I try to find x in terms of Y, so that when I substitute into the budget constraint, I am going to let wood Y variable instead of x variable, and then I have to find the value Y. Okay, so over here I would have x equal to okay, so if I swap the ratio on both sides of this equation, okay, then I will get x on y equal to py on 2 times alpha 1 minus alpha. Okay, so I just swap the ratio, and then so therefore x is going to be equal to py on 2 times alpha 1 minus alpha times y. Okay, so the purpose of doing this is I want x in terms of y, so that when I substitute into the budget constraint, I am left with an equation of y. Okay, so now if I substitute the 3 star into my budget constraint, then I will get 2. So my budget constraint is here, where 2x plus, and I know that x equal to py on 2 alpha 1 minus alpha times y, and plus py times y, and everything equal to 60, which is the income. Okay, so 2 cancel with 2, so what I'm left with is py times alpha 1 minus alpha times y plus py times y, and that equal to 60. So if I factorize it, and I'll take py times y out of the bracket, then inside got alpha 1 minus alpha plus 1, and that is equal to 60. And so py times y, now this is going to be alpha plus 1 minus alpha, everything divided by 1 minus alpha. Okay, and that is just 60. And so I got py times y, alpha minus alpha is just 0, so I got times 1 on 1 minus alpha, and everything is equal to 60. So from here I should be able to find the value of y, which is just 60 times 1 minus alpha, and everything divided by py. Alright, so as you can see, this is what the question asking you to show, and this is basically the demand function for y as a function of py. Okay, so this is the optimal amount of consumption of y that the consumer would like to consume to maximize the utility, and this is basically the demand, okay, function for y. Alright, so part B asking you to confirm that the elasticity of demand is equal to -1. So we got a demand function. It's very straightforward to find the elasticity of demand. So I got elasticity of demand formula is just, so it's basically just measure the change in the consumer demand given the change in price. Okay, so the formula is just going to be d q, okay, or dy on dp times p on y. Okay, so the change in the demand of wood y given the change in the price of wood y times the price of wood y divided by the demand of wood y. Okay, so we have a demand function over here. It's very straightforward. So this is just basically the inverse of the slope of the demand function. Okay, so I got y over here, I got py over here. So alright, so given that y equal to 60, 1 minus alpha, everything divided by py, then dy on dpy is just basically the differential of the demand function with respect to py. Okay, so if I differentiate okay, so I over here, as you can see, I got, so if I rearrange this to make, so 60, 1 minus alpha is just basically a constant. Okay, and py over here is just going to be, so if it's on a denominator, so if I want to move it to numerator, it's become py to the power -1. So by doing this, then you can see that it's easier for you to differentiate, because it's just basically the power rule that you need to apply over here. So if I differentiate this y function with respect to py, then the constant in front is just going to remain the same. Okay, so 60, 1 minus alpha remain the same, And if I differentiate this py to the power -1 with respect to py, then applying the power rule, I get -1 in front, and py to the power -1 minus 1. Okay, so that will give me 60, 1 minus alpha, negative in front, times py, -2. So that it just basically okay, 60, 1 minus alpha on py square. Okay, so if you move it back to the denominator, it will become a positive number, or if you want just to leave it like this, is fine. Okay. Alright, so we just substitute that into our elasticity, the price elasticity formula. So I got dy on dpy is -60, 1 minus alpha, everything divided by py square, okay, and times py, and divided by y, and knowing that the function of y is this, okay, 60, 1 minus alpha, everything divided by py. So now I just have to simplify this. So I got -60, 1 minus alpha, okay, everything divided by py squared, yep, times, so py divided by this, it will just become py times py. Okay, so the rule over here is that if I have x divided by a on b, then that will just be equal to x times b is divided by a. Okay, so the thing on the denominator, if you rotate or swap the ratio, then it's going to be become multiply to x. Okay. Alright, so it's similar over here. So I got py divided by the whole ratio. So if I swap the position, or if I rotate the ratio, then it's become py multiplied by py on 60, 1 minus alpha. Okay. Okay, so as you can see, I got -60, 1 minus alpha divided by 60, 1 minus alpha. Py times py is py squared divided by py squared, so cancel out, so I got -1 left. Okay, so the elasticity of demand is equal to -1.